Welcome to today's CWNP webinar, and the topic is Wireless Spectrum Analysis Tips. My name is Tom Carpenter, and I'm the CTO here at CWNP, and that simply means that I help to set the direction for our certifications, determining the objectives, determining the exam topics that should be covered, helping to manage the development of products and resources to help people gain the certifications, and so on. In the process of this, we want to help the community in every way we can by delivering relevant and useful content to them in the realm of 802.11 wireless LAN networking. And today's webinar is in that category because we're focused on spectrum analysis for 802.11 wireless LANs. Now, before we get into spectrum analysis, I'd just like to give you a review of the CWNP certifications. They offer career certifications in enterprise Wi-Fi technologies from beginner all the way through to expert. Not listed here, we have the CWTS certification, which is an entry-level certification for individuals like sales professionals, marketing professionals, and so forth. We also have our CWNA certification, which is the Certified Wireless Network Administrator. This certification is for those that desire to have a proof of knowledge for network administration, particularly wireless network administration. And then we have professional level certifications in three different categories: security, design, and analysis. Security, of course, is making sure that our wireless LANs are implemented and managed in a secure manner. Design is focused on how we design a wireless network in the first place so that it can be implemented well. And then analysis is all about troubleshooting problems when they occur. If you have those three professional level certifications, which of course would demand that you have the CWNA already because it's a prerequisite, then you can choose to apply for the Certified Wireless Network Expert. This is an elite certification status held by a little over 165 people, and it proves that you have not only passed the certifications, but that you have at least 3 years of enterprise experience in working with wireless LANs. To learn more about all of our certifications, simply visit the website at cwnp.com. So the agenda for today is to, first of all, get an overview of spectrum analysis. Why would we want to do it? Then we'll talk a bit about spectrum analyzers. What are the different kinds and how do we select the right one? We'll then deal with spectrum views. What are the views that spectrum analyzers give us of the RF spectrum? And finally, we'll talk a bit about some patterns in spectrum analysis. So first of all, an overview. When should you do spectrum analysis? And how do you identify spectrum problems? And the first thing you need to understand is that there's a difference between spectrum analysis and protocol analysis. Protocol analysis is all about analyzing the bits, the frames, that which is usefully communicated across the RF medium. But spectrum analysis is really just looking at the RF energy. We're seeing what is going on in the RF spectrum. Some statistics can be useful in determining if you should perform spectrum analysis. For example, in your protocol analyzer, if you see a lot of retries, say 25% retries, but yet there's low network utilization, this would tell you that maybe there's some interference that's causing corruption of your frames. You could see the interferers that are non-Wi-Fi with a spectrum analyzer. High CRCs, 15% or higher, or a high noise floor, meaning something is causing RF noise in the environment. A spectrum analyzer can help you to find all of these things. And then it may be that you're having application problems like intermittent problems, or maybe it's continuous. Geographically isolated, just one or two users in a particular area are having the problem. Maybe it's something that's difficult to replicate. You go and look at the situation, it doesn't seem to have a problem at all, but then you get back to your office and you're getting a call from the user immediately saying, hey, the problem's happening again. Maybe it's minimally noticeable, or there's absolute dysfunction in the area. The point is that at the application level, when you're having problems and you know the configuration is correct, in other words, everything you can configure about wireless is correct, then it may be that there's something going on at the RF layer. It may be that there's something at the physical layer that's a problem, and a spectrum analyzer could reveal that to you. Now, when we're dealing with spectrum analysis, it's important to remember some of the basics that you've learned in studying wireless networking so far. These include things like frequency, wavelength, amplitude, and phase. The frequency is the rate at which a complete wave cycle repeats. So a lower frequency wave versus a higher frequency wave. For example, 5 gigahertz is a higher frequency than 2.4 gigahertz. And then there's wavelength. How long is the wave? And basically, a lower frequency wave has a longer wavelength than a higher frequency wave. Therefore, 2.4 gigahertz has a longer wavelength than 5 gigahertz. Then there's amplitude. Amplitude is the strength of the wave. How strong or powerful is the wave or signal? And finally, there's phase, and phase is a factor of signals and not of unintentional radiated energy. Phase is the comparison of two waves. They can either be in phase or out of phase with each other. For example, with multipath in common indoor environments, two copies of a signal could arrive at a receiving antenna at the same time, and the two copies can be in phase or out of phase. When they are in phase, they are additive, meaning that the signal strength perceived by the antenna is greater or better. But if they're 180 degrees out of phase, they can cancel each other. If they're 90 degrees out of phase, they can be destructive of each other. The point is that signals arriving in or out of phase do have a determinate impact on the ability of that receiver to receive the signal. Now, it's important when we're talking about RF to think about how RF functions in the different domains. So we have the frequency domain and we have the time domain, and then of course there's amplitude in the frequency and time domain. The frequency domain is what we're looking at when we look at a real-time fast Fourier transform, or FFT, in a spectrum analyzer. We're looking at the wave, if you can think of it this way, like it's coming right at you. You're looking at the specific frequency as if it's coming right at you. Whereas if you looked at an oscilloscope, you'd be looking at something more like the time domain. And you might think of this as the wave if it's passing by you. So the time domain, the wave passing by you; the frequency domain, the wave coming at you. And you're simply getting spikes for the frequency to show you the energy level of that frequency. Now, it's important for us to talk about the different kinds of analyzers that are available to you. When it comes to analyzers, you have network analyzers, mobile analyzers, and integrated analyzers. The network analyzers are those that you use that have the big carrying cases in many cases, or they may be smaller. They've got a lot of knobs and buttons that you use to tweak them. The point is they're hardware based, and you can get them from a lot of different vendors to analyze the RF as it's traveling across a coaxial cable. It lets you see the signal that is being generated by the radio. But if you want to pull out of the air, quite often we're using mobile or integrated analyzers. And mobile analyzers include Metageeks, YSpy, DBX, Air Magnet Spectrum XT, Spectrum Expert. Ubiquiti had AirView there for a while, which was a very low resolution spectrum analyzer. But the point is that they are capturing the RF energy and letting you see that in a software application running on a computer. Integrated analyzers are, just as the name implies, integrated into access points. And in this case, you have things like Cisco Clean Air and many other vendors too. So the point is that the access point itself does spectrum analysis, and the spectrum analysis may be lower resolution than what you'll get with something like Air Magnet Spectrum XT, simply because of the fact that it is integrated into the AP. It may not have the same resolution, and resolution is just what level of frequency am I able to measure. So am I talking about a very small amount of kilohertz or a larger amount of kilohertz? And so what is the frequency width that I can measure when I'm dealing with resolution? So there are different types of analyzers, and here's the thing. Yes, you can use integrated analyzers in APs, but what those analyzers are telling you is what's going on at the AP. They really don't tell you anything about what's going on at the client, do they? So if I want to know what's going on where my clients are, I need a mobile spectrum analyzer. Now the good news is you might think, well, wait a minute, do I need to get a new spectrum analyzer every time there's a new version of 802.11? That is to say, do I need a new spectrum analyzer every time we go from 11N to 11AC to 11AX and so forth? Well, the answer to that is no. You do not need to get new spectrum analyzers every time, and the reason that you do not is because we're looking at the RF energy. We're not looking at frames. Now, it is important to know that the spectrum analyzer may do integrated protocol capture or protocol analysis. If that's the case and you want to use those integrated features, then yes, you may actually need to update the software, but your adapter should still work because the adapter just looks at the RF energy. And whether that RF energy is being generated as a single stream, 2 streams, 3 streams, 4 streams, it really doesn't matter. It's just RF energy. It may look a little bit different, but it's just RF energy. And so the answer to the question, do I need to update every time I move to a new version of 802.11, of course, is no. Now let's begin to talk about the different views in a spectrum analyzer. And the first view we'll talk about is the real-time fast Fourier transform. Real-time FFT is a measurement of amplitude over frequency. So it's the strength of the RF energy on a given frequency. Now, this can be a good way to identify the transmit mask, such as what you see in 802.11, but understand that it's not always going to look exactly like what you see in 802.11 because there's a sweep time, and because of the sweep time as well as the detail level of the particular spectrum analyzer you're using, or what we call the resolution, it may not look exactly like what you'd expect to see, but it's going to be close enough that you'll recognize it as an 802.11 pattern compared to something that's not 802.11, for example. But again, the thing to keep in mind is real-time FFT is right now what we're seeing in the RF space on a specific frequency. Now, different protocol analyzers will give you different views. They may allow you to see the average energy level over time. They may allow you to see the maximum, the minimum, and so forth. So they may give you different views, but the point is that in the various traces or histories of the real-time FFT, you'll see the current, and then you'll also see averages and maximums and things like that. Then we have the duty cycle, or what some call the utilization. This is going to show you how busy a frequency is. Now, each vendor is going to use its own duty cycle threshold to measure the percentage of time that RF transmissions are measured. It could be based on being above the noise floor, 20 dB above the noise floor, above neg 90 dBm. Here's the thing to keep in mind. You need to know what your vendor considers to be heavily utilized versus not. So for example, maybe they show you red if it's heavily utilized, but to them, red may mean 50% busy or 50% utilized or 50% duty cycle. You may not feel that that is so heavily utilized that you could not do something you're thinking of doing within that channel or that frequency space. So you need to know what the spectrum analyzer you're actually using reports as heavy utilization. Then we have the swept spectrogram view. Now this is the simple fact that your spectrum analyzer is going to sweep across the spectrum and then sweep again and sweep again. And it's going to have sweep times. How many times per second does it sweep the spectrum? And this is simply going to give you then a readout of the energy for each sweep. And some spectrum analyzers will use red for heavy energy, green for medium energy, blue for low energy, and so forth. With the swept spectrogram, sometimes called a waterfall view, you'll be able to see how RF looks in that space over time. And this is relevant to the duty cycle as well, because on the swept spectrogram, if you see it's just continually heavily utilized, that's a high duty cycle or high utilization, right? So the swept spectrogram is useful for seeing utilization over time or even duty cycle over time. So you can see, is there just a spike in busyness or utilization within the channel or within the frequency, or is this something that is continual all of the time? Then we also have spectrum density. Now this is one that's going to allow you to see the pattern because you're looking at the frequency domain. Remember, the frequency's coming at me, right? You're looking at the frequency domain and you're seeing the energy use within that frequency as well. And so you can see at the decibel level, the signal strength, how heavily utilized it actually is. These are sometimes called spectrum density views. It's kind of a combination of duty cycle and FFT so that you can really get a good, simple, all-in-one read of what's actually taking place in the environment. There are also, in many spectrum analyzers, features like time segment analysis. What this will allow you to do is record the activity in the spectral space over time and then go back at a later time and say, just show me what was going on between 130 and 135 or 140 and 145. This can be very useful if a user is saying they have sporadic problems. So you can take a spectrum analyzer, start it capturing in the space where the user is, and then walk away and go do other work. Then you can go back, having had the user write down a time when the problem occurred, and then another time again, and then you can go back in your history and you can actually view what was going on in the RF spectrum at that time. It may be that somebody in the next cubicle over is turning on a device periodically, and that device is causing some kind of interference. But the device is not on all of the time, and so the interference does not occur all of the time. So this is where time segment or historical analysis can really be very beneficial with spectrum analysis. Now let's talk a little bit about some patterns here before we get into a few tips in our presentation today. When we're talking about patterns, there are wideband and narrowband patterns. Wideband patterns are the kind of patterns we see with 802.11 channels. 802.11 channels are mostly 20 and 40 megahertz wide. You may see some 802.11 AC 80 megahertz channels, hopefully not too many of those in enterprise deployments. But even in an enterprise deployment, you may be in a business environment, but there may be some small business or apartment buildings nearby or anything like that that you might see 80 megahertz channels on. The point is 802.11 channels, 20 megahertz wide and wider, and you'll be able to see those with very distinct patterns. And hopefully you see a lot of them on 1, 6, and 11 in 2.4 gigahertz, but the truth is you're going to see them on 1, 3, 6, 7, 8, 11. They're all over the place because of auto channel assignment that just does a very poor job with many devices. And then narrowband, a good example of that would be things like video systems in some cases, Bluetooth devices. Even though they're narrowband, Bluetooth devices are going to hop all over the space, so we do see Bluetooth here, and we'll talk a little bit more about that as well. But the Bluetooth, and the thing to focus on right now, is that Bluetooth is all across the spectrum, but Bluetooth does attempt to avoid interfering with other systems. The way it does it is by detecting that a communication did not get through and then choosing not to send on that frequency again in the future. Of course, it has to communicate, and so it's simply the fact that if you're in 2.4 gigahertz, which is where Bluetooth is, and you're running 1, 6, and 11, and you've saturated your environment with it, Bluetooth is going to have to interfere some. And it may cause some frame retransmissions periodically, but remember, where Bluetooth is going to cause a problem is not on the reception of the frame at the AP, because there's usually less Bluetooth activity at the AP, but rather on the reception of the frame at the client. So you may see more problems with transmissions from APs to clients than you would from clients to APs with Bluetooth. And we'll talk more about why that is later. Here's an example of video transmission. Again, it does have some energy radiated across a wider spectrum, but the peak is certainly in a lower frequency bandwidth area. Here we see an example of a microwave oven. Microwave ovens can take out half or even all of 2.4 gigahertz, but thankfully their energy level is very low. So if you get significantly far from the microwave, usually 15 to 20 feet away, in most cases, the energy from it has diminished enough to where it won't cause major problems, but some leaky microwave ovens could cause problems even 30 or 40 feet away, though hopefully that is not the kind of microwave oven you're using in an enterprise environment or even in your home. More than likely, 10 to 15 feet is the range of a microwave oven causing interference, but I've definitely seen them cause problems on the other side of a wall from a cubicle or something of that sort. Just keep in mind that when that microwave oven is running, it's in 2.4 gigahertz, and it can certainly cause interference. And you can see that with the spectrum analyzer. You wouldn't see it with a protocol analyzer. So let's wrap up our presentation today with a few tips. Number one, interference happens where I am or where you are. Now, in this case, the I and the you is really my client and the AP. So interference happens at my client or it happens at the AP. It doesn't happen in between. The energy strength of the interference at the point of reception is what matters. So if I'm sending to the AP and there's some interferer at my location, that will not cause a problem with the ability to transmit to the AP as long as that device has a low enough energy footprint that my energy detect doesn't see it. Now that energy footprint could be low enough that my energy detect ignores it, but it could potentially cause corruption with my frame on reception. So the point is that interference happens where I am or where you are, not in between. If there's something generating RF energy 30 feet away from me, but by the time it gets to me, it's so low as to not cause problems, and by the time it gets to the AP, it's so low as to not cause problems, I'll still be able to communicate with that AP. But a client closer to that interfering source may indeed have frame corruption problems, and we would need to go to where that client is and find that interfering source, and resolve the issue. Realize that if you're trying to use a spectrum analyzer for location purposes, directional antennas can help. And a lot of your mobile spectrum analyzers, like your Magnet Spectrum XT and MetaGeek, can use external antennas. So you can connect a directional antenna to it, and then you'll be able to better find interfering devices and narrow those down. And finally, keep in mind and always remember that only spectrum analyzers can see all non-Wi-Fi activity. So if you want to be able to see the non-Wi-Fi activity, you're going to need that spectrum analyzer. Now you might run into a specialty adapter somewhere that says you can do Wi-Fi and Bluetooth all in the chipset and things like that. But the reality is, if you want to see non-Wi-Fi, you need a spectrum analyzer because it looks strictly at the RF energy. Now, while the Q&A will be cut out for the posting to YouTube, we do want to open it now for questions that you might have to be able to answer those questions for you. For those watching on YouTube or those not able to stay for the Q&A, thank you for viewing this CWNP webinar presentation.